So I guess we should get started. Good morning, everyone, or good afternoon. Good afternoon here in Atlanta. So welcome to the next seminar in our AI4OPT seminar series, and thanks for joining us virtually. Today we have Dr. Satyan Kale from Google Research. Satyan works as a research scientist in Google Research at New York, and his research interests are broadly in machine learning and optimization, which is basically the focus of our institute. More specifically, he works on decision-making under uncertainty, statistical learning theory, combinatorial optimization, and continuous optimization. He's received several awards, including the ICML 2015 Best Paper Award, ICLR 2018 Best Paper Award, Best Student Paper Award at COLT 2018, and he also served as program chair for COLT 2017 and ALT 2019. So today he's going to talk to us about federated learning in presence of heterogeneous clients. So without any further ado, Satyan, the floor is yours.
All right. Okay. Thanks, Shivatisha. It's a pleasure to give a talk here. I'm sorry I actually could not visit in person. I would have liked to do that, but given the existing pandemic situation, I will be trying to limit my travel. But it's still definitely a distinct honor and pleasure to give this talk virtually and meet with some of you after my talk. So I have this talk presentation going on, and I don't really see anybody. So if there is any question, please feel free to interrupt by just raising your voice. I will probably not be able to see any raised hands or anything of that sort. This talk is designed that I can, in a sense, I can like stop it at any point. So don't worry about interrupting me at any point, and if you need more clarifications. Okay, so let me just get going. So as Shivatisha mentioned, this talk is on optimization algorithms for federated learning, specifically in the presence of heterogeneity in the clients. And I'll describe what all of these terms mean as we go along in the talk. But first, I would like to acknowledge my co-authors on this sort of series of work. The main work was actually done by Praneeth Reddy, who was my intern for a few summers at Google. Also, we had collaborators in Martin Jaggi, who's at EPFL, who's Praneeth's advisor, Meghal Mori, Sashank Reddy, Sebastian Stish, and Anandatirtha Suresh, who are at Google. And sorry, Sebastian Stish is also at EPFL. Okay. So I'm going to start by describing the federated learning setting. I'm not sure how many people are actually familiar with the federated learning setting, but I apologize if most of you are familiar with this, but I just wanted to have everybody on the same page. So this is a very ubiquitous optimization scenario that is common these days at places like Google, where we want to train a machine learning model, say, using a lot of data that resides not on any central server, but on several client devices. So for example, you might want to train a language model, for example, using data that resides on clients' mobile phones. Or you might want to train a classifier for some medical diagnosis using data that resides on hospitals. So there are obviously privacy concerns due to which you cannot actually transfer any data from the client to the server. So the goal is to try to train a model in the face of such constraints. So basically, we want to be able to train a model using this client's data without transferring any data to the server. And also, there are obviously many communication constraints and so on and so forth, which I will discuss as we go on. Okay. So roughly speaking, the way it works is as follows. So the server maintains some model, some global set of parameters X, and in each round, a certain subset of clients are chosen. So I represented them by these clients down here. Then the global model is shipped to all of those clients. And the clients themselves have first of all, they have their own data, but they also have some computational capability. For example, mobile phones can do some computation themselves. So you send the server model to the clients, and then using the local data on the clients, you update the global model. So you basically, you can imagine taking some gradient descent steps on the global model using the local data, and then the clients ship the model updates back to the server rather than shipping any data, they just ship updates. And at the server level, all the client updates are aggregated, and then the server model is updated based on the affiliates. So that's roughly how federated learning works. Um, and a few characteristics of federated learning which make it difficult compared to normal distributed optimization is that there's a high communication overhead per round. Furthermore, there's only a few clients can participate in each round of federated learning. So in particular, if you think of the clients as being mobile phones, only some of them are active participants in each round. Typically, these computations happen, for example, when the phone is plugged in at night and the phone is charging. So across the world, different mobile phones are active at different times of the day. So only a few clients participate in each round. And the primary challenge that we were concerned with in this work is that the data on the clients is pretty heterogeneous. The different clients typically have very different data, or you can imagine that they are drawn from different distributions from the different clients. So this is again easy to see why this is the case, because if you think of, like, for example, the mobile phone setting, the data tend to be very different across the world. So those are a few characteristics. I'll pause here for just a few seconds to see if there are any questions. Again, please speak up because I can't see anybody.
So I have a question, Satyan. So
Yeah.
why don't you send the data to the server and make the changes to the model there itself, as compared to doing that in the client computer, because that's not a powerful computer, right?
The primary reason we can't do that is privacy concerns. So for example, if the clients are like mobile phones, the data that is stored on the clients is their own private data, and we have definite privacy concerns in actually transferring any of the data to the server. Like, if you knew that your personal data was being transferred to, say, Google's server, I think you might not be comfortable participating in this kind of data sharing. So that's the primary concern. Furthermore, there's also communication constraints. Typically the bandwidth of the connection between the clients and the server is very low. So actually transferring a lot of data between the clients to the server is expensive, and you cannot always do that. It's on the other hand, it's much easier to actually ship some parameters of the model over to the clients and have the clients actually do the computation themselves based on their local data. So that's a good question. I mean, I hope that answers it. But if there are any more
I have another question. So, yeah, sorry.
Go on. Yeah.
So where is an example where this federated learning, what kind of model do you learn from this? What's the application of this?
Okay, so one, I mean, it's basically deployed on any kind of, I mean, at least at Google, we essentially it's deployed for any kind of model that you would imagine training with user data. So I think one application that I can mention is the Google keyboard. So the Google keyboard is kind of predictive, like it will basically give you suggestions of what word you want to enter in your text for every when you start typing into the phone. So this kind of model is trained using federated learning. Again, because a lot of users have their own maybe vocabulary that they want to use, and training a model by combining all the data is just not feasible. So this is one application, for instance.
Hey, Satyan, I have a quick question.
So if there are no more questions, I will continue. Okay, so I want to distinguish between two different settings of federated learning, and actually these two settings are. It's important to understand the difference between these two settings, because the kinds of algorithms you can develop for these different settings are quite different. So there are two main settings. So there's one is called a cross-silo federated learning, and the other is cross-device federated learning. So the cross-silo federated learning, you should think of it as a setting where the number of clients is very small, let's say to 200. And these clients tend to be big institutions, such as say hospitals or financial organizations. And there is a large amount of data per client. And furthermore, these clients tend to be persistent, meaning that you're almost always available. You can pretty much always connect to them. You can always address them. And also, these clients tend to be stateful, meaning they can actually carry state from, say optimization state from round to round, and you can take advantage of that. On the other hand, the cross-device federated learning setting is the one that is more common. Here you have an extremely large number of clients. So, for example, like something like 10 to the 10, if you're looking at say mobile phones. So these settings typically involve things like mobile phones or Internet of Things devices, and typically there's only a small amount of data per client, unlike the cross-silo setting. And these clients tend to be transient. I already talked about this. So only a fraction of clients are available at any time. And typically, you might see a client once, but you might not see them ever again. So because of that reason, they also tend to be stateless, meaning you cannot actually store any state on the clients because they might never again participate in federated learning. So you cannot really, I mean, there's no point of actually storing any state either. So there are these two big differences. And for the first part of my talk, I will focus on the cross-silo federated learning. So where, again, now you have a small number of clients with a lot of data, and the clients are persistent and stateful. Okay. All right. So in order to try to develop algorithms for the setting of federated learning, we need to develop some kind of mathematical formalism. So the way we do it is the following. So it's the objective that we want to minimize in federated learning is the following. So we want to minimize an average over all the clients. I'm not sure if you can see the cursor, by the way. So just let me know if you can't see it. But you basically want to optimize an average of expected losses. So essentially, for each client I, you have a loss function fi, which depends upon the local data of the client that's represented by this the letter C here. So this is the expected loss of the parameters x on the data for client I, and you want to minimize an average of all of these expected losses, okay, over all possible model parameters. So roughly speaking, that's how we will formalize the cross-silo setting. So essentially, this expectation refers to the fact that there is a lot of data on each client. So you can imagine that essentially you're directly minimizing population loss, and since you have a few clients, you're just going to optimize the average of all of their losses. Any questions about the formalism?
So what's the uncertainty here? So why are you taking expectation?
The uncertainty here is over the data distribution on each client. So the data for each client are actually drawn from different distributions, and so that is why you have some stochasticity.
Okay.
All right. Okay. So let's. Okay. So I guess this is what I just mentioned. Okay. So yeah. There's another question. Yeah.
You said the data from each client comes from a different distribution?
That's right, yes.
But you didn't specify I for the distribution, right?
That is right, yeah. I'm being a little bit loose in my, in my notation here. So in this expectation, I should have written expectation over C drawn from some distribution DI, which depends upon the client I.
Satyan, I have a quick question.
Sure.
Do you assume the presence of DP noise for this work?
Sorry, what do you mean by DP noise again?
Oh, differential privacy noise. Like I think some federated learning.
Oh, I see. Yeah,
noise to the gradients.
That's an excellent point. Like, yeah, that's absolutely right. So in order to, that's kind of an orthogonal consideration to the work that we are doing here. We don't actually consider noise that is added due to differential privacy. So here we're just simply focusing on doing non-private optimization and simply just minimizing the average of these expected losses.
Okay, so I suppose, I guess, in this case, the privacy properties are coming simply from aggregation over several clients in that case?
Yeah, actually, we don't make any claims to privacy for these algorithms because it's simply like sort of classical non-private optimization in this case.
Okay.
If you want to additionally have privacy guarantees, then you're right. You do have to you do have to add some amount of noise to the gradients in order to make so whenever you're communicating some updates, you have to essentially add some amount of noise to the updates in order to make them private.
Okay, sounds good. Thank you.
Okay. All right. Cool. Yeah. I mean, yeah. So basically, we're only looking at the optimization setting just to have a clean understanding of this. Obviously, in real world system, you obviously need to have differential privacy. So yes. So thanks for the question. Okay. So I'll move on to algorithms for this setting. So if you start thinking about it, the simplest algorithm you can come up with is the following, which is just stochastic gradient descent. So what we can do very simply is for every client that you have sampled, that's every client in the set S out of sampled clients, you compute a large batch stochastic gradient and average stochastic gradients. Okay, so what you do is basically you take let's say up to capital K samples from each client, average the stochastic gradients evaluated at the point X. So GI of X is a kind of a short form for a stochastic gradient of the loss function Fi evaluated at the point X. So you average the number of the stochastic gradients in order to reduce the variance, and then you just simply update the global model by averaging these mini batch stochastic gradients over all the sampled clients. Okay, so that's stochastic gradient descent, and it's obviously equivalent to synchronous centralized large batch training. So essentially, in each step, you just basically gather all the stochastic gradients from your clients and then update the global model using the average stochastic gradient. So essentially, it's doing centralized training with gradients that are obtained from the sampled clients. The one drawback of this approach is that it is very slow. Essentially, we do just one update to the global model X in each communication round. So in every communication round, we have to average all of these gradients and then send them back to the server, and the server just takes one update step. So this tends to be very slow, especially when communication is a bottleneck. Okay. So the algorithm that is actually deployed very widely in practice is a very easy and intuitive extension of this distributed SGD method. This is called Federated Averaging, and it was introduced by McMahon et al. In 2016. So here, what we do is we observe that the clients have some computational capabilities. So on each client in the sample set of clients S, we instead of just simply averaging case stochastic gradients, we instead perform case steps of stochastic gradient descent. So essentially, on each client, we will repeat the stochastic gradient update k times. So we'll start with the global model and take k steps of stochastic gradient descent, and then just ship the final updated model to the server, and the server simply aggregates the final models by averaging them. Okay. So what are the benefits here? Potentially this could be faster because essentially the clients are doing a number of descent steps in each round. So for every communication round, each client does k updates of stochastic gradient descent. So potentially we might expect faster conversions compared to just stochastic gradient descent. However, we note that because the clients have very heterogeneous data, meaning the data are actually drawn from different distributions, these stochastic gradient steps here are actually just optimizing the local objectives, and they're not actually optimizing the central objective that we want to minimize. So we might expect to start seeing some kind of drift from the central objective, and so you might not actually converge to the right thing. So we don't actually have a proof of convergence here in this case. Okay, so So that's the kind of the pitfalls and benefits of this method, and it works really well in practice. So it is deployed, but so here what we want to fix is the second part, which is that we might actually not have a proof of convergence because the clients are doing stochastic gradient descent on very heterogeneous data. Any questions so far?
So X are weights, right? But it's not
Yeah.
the data, but okay.
So what is the question?
So the question is that the X variables, they denote the weight, right? But usually X variables, they denote the input data.
Yeah. So here I'm kind of hiding away the input data points, but here I'm just using optimization notation where you usually denote the optimization variable by X. In machine learning, typically you would call you use the notation W for the parameters, but yeah, I'm just using X because this is more optimization oriented.
Excuse me. Okay, you can go on.
Another quick question. So you said it may not converge. Do you mean it might diverge, or it does not converge to the global optimum?
I actually mean that it may not converge to the global optimum.
Okay, it converges.
Yeah, the convergence is not guaranteed. It may not. It may not necessarily diverge, but it may not converge either to the right solution. You can actually make it converge if you start making the step sizes small, and I'll talk a little bit about that later on. But if you just kind of think of a fixed step size, then you actually may not have convergence also.
Okay. And is it due to the stochasticity you're talking about, or due to just this heterogeneity?
It's mainly due to heterogeneity. Like even if you did not have any stochasticity, you can still come up with very simple scenarios where you might not have convergence. I'll illustrate these concepts with a picture later on, so hopefully that will become more clear.
Okay.
And
Okay.
Just one more question. So when you update the weights at each client, so you are taking the gradient using those weights only. So in some sense, you are saying that the weights across different clients, they are disjoint. They are not dependent on each other. But
at least in the beginning they're going to be the same. Before we start, so they're going to be initialized to the same set of weights from that are obtained from the server. But once you start doing the steps of stochastic gradient descent, they might start diverging from each other.
Okay, got it.
Okay. All right. So so I will move on to our fix to this problem. So so this was okay. I mean, it's not quite new anymore, but we developed an algorithm called a scaffold, which it's a kind of a convoluted acronym which stands for stochastic controlled averaging for federated learning. But anyway, so the way we will fix this problem of bad convergence is by introducing correction steps. So essentially, what we do is we take the we take the stochastic gradient update as before, but then we add these correction terms here. So this I'll explain these in a little bit. But the role of these correction terms is to ensure that the divergence of the client updates is kind of bounded, or at least it is controlled in some manner. So I'll explain what these terms are later. So essentially, we take case steps of these controlled stochastic gradient descent steps, and then in the end we ship all of these updated parameters to the server, and the server simply aggregates them by using averaging as before. Okay, so that's the new algorithm. I'll explain the details in a minute. Okay, so this is the correction term. So as before, we might expect to see faster convergence because in each communication round, we are performing case steps of stochastic gradient descent. And because of this correction term, we can actually show theoretically at least that that the updates that are induced due to this essentially mimic centralized updates. So therefore, we will always converge to the right solution. So that's the high level view of what this algorithm does. but I'll go into some more details on the next few slides. Okay, so in order to understand this correction term, we need to first understand when does FedAvg fail. And here's the okay. So it has been noticed in several papers in the past that federated averaging degrades more and more heterogeneous clients, and the reason for that should be pretty obvious. So so here's kind of a cartoon picture of what happens here. So suppose you just have two clients, and let's plot the contours of the objective of the first client over here, and then the contours of the objective of the second client over here. What we want to try to optimize is the average of these two functions, these loss functions f1 and f2, and the contours of that average look like this in the green here. So notice that the optimum for the first client lies somewhere around here, and the optimum for the second one lies somewhere around here, whereas the optimum for the average lies somewhere in the middle. Okay. Now, once so if you're running the stochastic gradient descent, meaning you just take one gradient descent step on each client and aggregate them, then we are just simply running global stochastic gradient descent, and so we know that the limit point of stochastic gradient descent is going to be the true optimum point here. Okay, so essentially we take one stochastic gradient step or gradient descent step on each client, and then when we average those gradient steps, we take a step roughly in the right direction. And eventually, after taking multiple steps, we will converge to the true solutions. So stochastic gradient descent is the theory is well understood, and we know that it does converge to the optimum point, at least in convex cases. So let's see what happens when we start doing multiple local steps, meaning federated averaging on the clients. So when we do federated averaging, so in the first step, as we discussed, if you just average the updates after the first step, you will still get a point that is roughly in the right direction. But once you take the next step, essentially you're going to start diverging even more from the path. So when you take the second step, for example, on the first client, you kind of go closer to the optimum of the first client, and on the second client, you go closer to the optimum of the second client. And then when you average the updates after the second step, you're going to get a point which is roughly around here, which is now starting to diverge a little bit from the path going to the optimum point. Okay, and this problem obviously becomes worse and worse as we take more steps. So after the third step, for example, you're going to get on the first client, you're going to get closer to the optimum of the first client. Same thing for the second client, and when you average them, you're going to get you're going to get a point that is even further away from the path going to the optimum point. So this is the reason why federated averaging might fail. So in fact, the problem is even worse. So if you actually you can come up with situations where if you even start at the true optimum solution, meaning like you actually initialize the updates to be the true optimum point, even so, if you start doing federated averaging, you're going to start diverging, meaning in the first client, you're kind of going to start going towards the optimum of the first client, and in the second client, you'll basically diverge away from the optimum to the first one. So yeah, and then when you average, basically when you average the final iterates, you're going to get some other point here, which is going to be different from the true optimum point. Okay, so I mean, this is kind of a cartoon explanation about which explains why federated averaging does not converge to optimum, and we can also formalize all of this stuff. In order to actually reduce the distance between the point that we will converge to and the true optimum, we need to have a very small learning rate. Okay, so again, like I said, this can be formalized in the case of stochastic gradient descent. If you so here's a little bit of notation. If you do R communication rounds and K local steps and go to the clients, and let's say we are also working in a smooth and strongly convex setting where L is the smoothness parameter and U is the strongly convex parameters, and sigma is the variance stochastic within the client, then we can write down a convergence rate for a simple stochastic gradient descent in the following way. So this is basically the suboptimality decreases in an expression that is given here. essentially the noise variance decreases at the rate which looks like sigma square over RKN, and then the bias goes on at an exponential rate, which depends upon the condition number. So this is all very standard optimization theory. For non-convex functions, you don't actually have convergence guarantees, but you can show guarantees in terms of the norm of the gradient. And again, here you have the noise decreasing at a rate which looks roughly like 1 over square root r, the number of communication rounds, and the bias reducing at a 1 over r type of rate. So this is the standard theory for stochastic gradient descent. So in order to actually describe the rates of convergence for federated averaging, it is convenient to kind of just hide these the noise variance terms which arise due to noise, and just call them n for convenience. And then what we can show is that So in order to actually prove a convergence guarantee for federated averaging, we need to assume that the clients are not too heterogeneous. So we need to come up with some measure of heterogeneity between the clients. And the particular one that we use is the following. So here we assume that roughly speaking, the variance of the gradients on the clients is bounded by the mean of the norm of the mean, essentially. So it's a little bit technical. I don't want to go into too many details unless somebody is interested, and I can definitely talk about that. But roughly speaking, this is an assumption which assumes that the clients are not too dissimilar. Essentially, this gives you a bound on the variance of the clients. So if roughly speaking, if the variance of the clients is bounded, then you can show that federated averaging will converge. And in fact, the rates that you get look like the following. So essentially, you get the same rate as stochastic gradient descent rate, but you have an additional term here which depends upon the roughly speaking the variance of the clients. So notice here that this extra term here depends upon g square, where this g square is some sort of proxy for the variance of the clients. Okay. So the overall takeaway from the slide is that you can show convergence for federated averaging if you assume that the clients have bounded variance and you also make the learning rate small enough. But the price that you pay is an extra term in the convergence rate compared to stochastic gradient descent. Any questions about this?
Yeah, I have a question.
Yeah.
So I don't know if you're going to mention later, but how are you going to pick the C's and how are the C's updated?
Yeah. I'm going to come to that. I haven't actually talked about the guarantees for the scaffold algorithm yet. So far we're only looking at federated averaging, trying to understand why it doesn't converge and how can we actually bound the divergence of federated averaging and then use that insight into designing the new method that I described earlier. Okay. All right. So I'll come to that in just a minute. So let me actually skip this part for now. It's more talking about convergence rates. Okay, so one point I would like to make here is that even though this is an upper bound that I just showed you on the convergence rate, this extra term that appears here in the convergence rate is inherent, meaning like we have a lower bound which roughly matches the upper bound as well. So it is possible to construct a scenario where the clients are bounded variance such that federated averaging will always have at least this amount of suboptimality. So I won't go into many details of this unless somebody is interested, but I can discuss it offline as well. So let me let me move. Okay, so I'm going to move directly to scaffold, the correction that we use for federated averaging. So the idea, as I mentioned earlier, is to use these control-variates or correction terms in order to make sure that the updates stay on the right path to the optimum point. So roughly speaking, this is the intuition behind the variables C and Ci. So what we're going to do is we're going to somehow guess the direction of the server updates, and we're going to call it C. So roughly speaking, we're going to guess which update we should make to the server model XT in order to move closer to the true optimum. and we're going to call that C. And then we're also going to make a guess of the direction of the client update. We're going to try to figure out how much drift we are going to get from the correct central path because of the heterogeneity in the clients, and we're going to call that CI. And then we're going to apply a correction which looks like C minus CI. So essentially, what's happening is the heterogeneity in the clients is causing you to drift away from the central path which goes to the true optimum, and we're going to subtract out that drift by this negative CI term, and we're going to ensure that you kind of continue to move in the same central path by adding this C term there, okay, which keeps you on the correct path. Obviously, all of this relies on these guesses being accurate. So I will also describe how to actually get these guesses in a reasonable manner. But at a high level, the idea is simply to basically remove the drift that you get due to heterogeneity and add back in the kind of a direction towards the true optimum point. Okay. So that's the effect. So basically, what happens is, like, if you move away from the path, the negative CI term puts you back on the true path, and then the C term actually makes you move in the correct direction. So at a high level, this is the intuition behind the control variates. So now the question arises how to actually compute these correction terms. So sorry, let me just kind of skip this part. Okay, so the way we will do it is to actually use historical data. So it's quite simple. So essentially, when we take multiple steps of stochastic gradient descent on each client, we are going to set CI to be simply the average of all of the steps that we have taken in the previous communication round when we saw this client. So roughly speaking, we're going to take CI to be just the average of the stochastic gradient steps that we took in the previous iteration, and we're going to take C. Okay, so we're going to do this for both clients. So for the blue client, we're going to take the average of its own local steps, and for the red client, we're going to do the same thing. We're going to take the average of those, and then the guess for the central direction C is going to be simply the average of the control variate for the blue client and the control variate for the red client. Okay, so these are statistics that we're going to compute in each round of the algorithm, and then we're going to apply these statistics in the next round. So in this way, we're going to kind of use the previous round as a means of guiding us in the same direction, and then use that in the next round. Okay. Does that make sense? I might have rushed a little bit through this, but I'm happy to pause now and explain a bit more.
I have a quick question. So this correction, I suppose it can be applied both on the servers and or the clients end. Is that correct?
Sorry, can you
so
the
correction term that you're introducing, or the control variables,
that's
is there a constraint
point,
on where it needs to be added?
Yeah, I mean, I think that's an excellent point. Actually, you can actually potentially apply it on the server level as well, and I think that could also work, but I don't think you're necessarily tried it. Okay, so I think intuitively it makes more sense to apply it at the client level. Maybe I should have actually gone back to the previous slide, because the idea is that is to try to keep the client updates roughly along the central path to begin with, so that they don't drift too much from the central path. So basically, if the client is going to do 3 steps, then after each correction step, you're basically roughly going back to the central path again. Whereas if you don't do the correction at each step, you're going to kind of start drifting towards the optimum of the of the client itself. So if you apply the so essentially we are forcing each step on the client to come back to the central path before taking the next step. Whereas if you just do update at the server level, you're going to get a lot of drift that accumulates, because each client is going to start drifting towards its own optimum point, and then it will be very hard to undo that big drift at the server level.
That makes sense.
yeah, my intuition about why it might be hard to apply at a server level, but I don't think we've analyzed that that idea. That might well very well work as well. Okay.
I have a question. So this C minus Ci term, you add this to minimize the drift from the central path, right? So how do you decide? How do you decide the weight? So this is just a direction where you want to move, but how much do you move in C minus Ci direction? How do you decide that?
I mean, we just simply add it, there's no weighting involved here. So we just basically add the C minus Ci term directly to the stochastic gradient. So the idea is that basically this negative Ci term will essentially counteract the drift that you're getting through this stochastic gradient, and the C term will kind of keep you on the central path.
So like, what if in the direction, like the magnitude is small, so it's just equivalent to adding nothing. So how do you decide what kind of, like, how much it should be in magnitude so that it gets back to the central path?
Yeah, I'm not sure actually quite understand. I mean, the magnitude of this correction doesn't matter so much. It's we just basically add it directly with weight 1, so to speak, because the idea is simply that the CI should be roughly speaking a guess of how much the drift in GI is, and so we will subtract that out. So that's really all there is to it.
Okay.
Yeah.
I have a quick question.
Okay. Yeah.
Yes. So as I understand, like under BG assumption, FedAvg also converges with slower convergence. But is there any other assumptions? Yeah. Is there any other assumptions like FedAvg does not work and only work for scaffold, something like that?
Oh, so sorry. So I think you can analyze federated averaging using different assumptions. I think there are like various different metrics people have proposed to actually analyze federated averaging. I mean, we just proposed one like a fairly simple assumption that is seen in practice in order to analyze it. Yeah. But I mean, I guess I should have made this more clear, but the analysis of federated averaging actually does not have any connection with that of scaffolding. So maybe I should actually jump quickly to, I don't know if I have, okay. So I'm going to jump directly to the convergence rate. So it turns out that we can also prove a convergence rate for scaffold, and the convergence rates are given here. And notice that there is no assumption made here regarding the variance of the clients. So here essentially we can show convergence without its extra term that was there in the case of federated averaging. So basically the addition of these correction terms actually automatically guarantees that you can converge regardless of how heterogeneous your clients are. And you have a convergence rate which basically is better than federated averaging.
Okay, thank you.
Okay. All right. So let me maybe go back a little bit. Okay. So we also did a few simple experiments, and in practice we do observe that it converges faster than. Okay, so even though our convergence rate is the same as SGD, it actually does converge faster than SGD in practice. So it's simply because it's taking multiple local steps in each round. Okay. Let me see check the time. So I have about 15 minutes left. So I'm going to skip this a little bit and jump to. Okay, so as I said, we ran a bunch of experiments, and it turns out that scaffold works better than federated averaging in pretty much any scenario you can think of. But I'm going to move. Okay, so the takeaways for scaffold. So first of all, the observation is that the degradation of convergence in federated averaging is due to client drift. And if you want to use federated averaging, then you need to kind of have small step is on the client, and you need to separate the server and client step sizes. And in case you can, I mean, you can afford. So okay, so the one kind of drawback of Scaffold is that it requires you to store these control variates, these C and CI variables on each client. So it automatically needs the clients to be able to store some state, and therefore it only applies in the cross silo setting of federated averaging, sorry, of federated learning. And in those settings that you can afford to store state on the clients, you should probably use Scaffold, because in experiments you have seen that it converges faster than SGD and federated averaging, and it is also resilient to heterogeneity in client sampling. So regardless of how heterogeneous your clients are, it still converges fast. Has the same convergence rate. Yeah, as I mentioned, it requires maintaining client state, so it only applies to the cross silo setting. Okay. Any questions about this part? Okay, I will move on to the next part. So now we'll turn to the more common cross device setting of federated learning. So in this case, you have a very large number of clients, for example, like mobile phones and so on. And you only have a small amount of data per client, and the clients are transient and stateless. So you actually cannot apply Scaffold to this setting because the clients cannot store any state on them. Okay, so I'm going to describe a framework for developing optimization algorithms in the cross-device setting. So first of all, again, we need to formalize the cross-device setting. So here it looks very much similar to the cross-silo setting, except now the roles of the averaging and expectations are reversed. So because the clients have only a small amount of data, inside the optimization, the inner optimization is simply an average over the client's data points. And then since we have a large number of clients, we imagine that the clients are drawn from some distribution D. And then on the outside, we have an expectation over a random client drawn from the client distribution. And again, we want to find a set of parameters X, which minimizes the expected of all of these expectation of all of these average losses over the client data. Okay. So that's kind of a minor difference. I mean, you have like an average over like a small number of points on the inside versus on the outside, and you have an expectation on the outside instead of the inside. So, but kind of mathematically, there isn't really any difference between the two formalisms. Okay. Let me move over that. Okay, so the idea for developing algorithms in the cross-device setting comes from looking at SGD with server momentum. So this is a very intuitive way of running federated averaging with momentum. So here's how it would work. So let's assume that we have only one client per round. So basically, what we want to do is we will take one gradient descent step on the client, and then essentially send that gradient descent to the step to the server, and the server is going to update its own parameters by aggregating, in this case, only one gradient step and adding a momentum term here. And the momentum is updated by the usual way, where you take the previous momentum and multiply by some momentum parameter beta and adding the new gradient. Okay, so this is SGD with sort of momentum. Again, because SGD with sort of momentum, centralized SGD converges, we know that there's guaranteed convergence here. But just like standard SGD for federated learning, this communicates on each round as well. Each client is doing only one descent step, and so it can be potentially pretty slow. Instead of that, you can think of the clients running multiple steps with momentum. So here's how that would work. Sorry, not the clients running, the server running with momentum, but you simply take multiple steps on the client as before. You take k steps, and then you look at the difference between what you started from and what you ended up at each client, and treat the difference of these two as some sort of pseudo gradient. And at the server level, we take one step with this pseudo gradient, and then in addition add a momentum term here. The momentum is again updated in the same way as before. Okay, this is called Federated Averaging with momentum. This is not at all work. I'm just mentioning it as prior work. This method again communicates only every k updates. Remember that each client is now doing k steps just like Federated Averaging. And it may have the problem that it may not converge because the client drift causes these updates to kind of diverge from each other, and so it may not actually converge to the true solution. However, I mean the addition of this momentum term here does help try to counteract a little bit of this drift, and but still you might have bad convergence properties. Okay. So the new algorithm that we came up with is called Mime. It's called Mime because the idea is to mimic any centralized optimization method in the federated setting, and I'll come to the general setting in a little bit. But first, let me describe how the Mime algorithm with momentum works. So what we're going to do is it's very simple. We want to ship the momentum that you computed at the server to the clients, and each client is now going to do k steps of stochastic gradient descent with a fixed server momentum. Okay, so basically we add in the server momentum for each update to the client, and at the server it's very simple. You again aggregate all of these updates as before, and then you just update the server momentum by taking computing the gradient at the server parameters and adding it to data times the previous momentum. So at a high level, the momentum is computed globally at the server, and it's applied locally at each client in each client update step. Intuitively, what is happening here is that even though there is some client drift due to heterogeneity in the client gradients, the addition of this fixed server momentum at every client mitigates the drift a little bit and enables you to converge to the right solution. Okay, so again, the benefit here is that because you're doing k updates in each round, you might converge faster. And again, as I mentioned, you reduce the client drift, the drift that you get in this using this fixed server momentum. This idea of computing some momentum type terms at the server and applying them on each step of the client updates also extends very similarly if you want to use, instead of aggregate momentum, but a different method like Adam and so on. So all of these methods can be adapted very easily to fit this framework. Okay. So this is kind of a pictorial representation of what happens if you just run federated averaging with momentum. So roughly speaking, all of the clients kind of start drifting from each other, and they converge to essentially different points. And then when you average them out, you might end up at a point which is the average of the true optimum, the x1 star and x2 star. But what Mime does is that by the addition of this fixed momentum term here, it forces the updates of the clients to kind of stay more or less in sync. And so when you average the final updates, you end up at a point that is fairly close to the true optimum x star. It may not actually be exactly x star, but it does stay closer to the true optimum. So that's kind of a pictorial representation of how adding the momentum helps here. Okay, so I think I'm running out of time pretty quickly, so I'm going to maybe just skip a few slides. So roughly speaking, what we're saying here is that there is a way to break up any centralized optimizer, such as Adagrad or Adam or SCAFFOLD momentum, into different updates, which updates the parameters and which updates the state of the optimizer, and then do the state update on the server and the actual updates on the clients using the same state at each client. So this is a very clean division of labor between the server and the client. And for all of these different variants that you can write down, we can provide convergence guarantees. Okay, so I'm going to again skip all of this stuff. We also have convergence guarantees for these methods, and what we can show is that these methods that we developed, MIME, SCD and MIME momentum with variance reduction, actually obtains faster conversions than server-only methods like SGD or momentum with variance reduction. The improvement is actually in lower order terms. So the higher order terms stays the same, but the lower order terms goes from L over epsilon to delta over epsilon. So I don't have time to go into details of what's going on here, but roughly speaking, we can improve over just running things at the server, and the analysis also gives you a prescription for how many steps you should take at each client in order to get these faster convergence rates. Okay, again, in experiments, we do see improvements over just running like SGD with momentum at the server, for example. Okay, so the takeaway from this section is that momentum injects global information and helps reduce client drift. So essentially, using the same momentum in each client update enables you to stay in sync with all other clients and reduce the problem of client drift. So the simple idea here is to compute momentum globally at the server, but apply it at each during each client update. And analysis also yields some bounds on how many local steps you need to take in order to obtain faster convergence rate, and it depends on some notion of Hessian variance, which I unfortunately didn't have time to get into. So that's all I have to say for today, and I'll stop here and take any questions.
Let's thank Satyan for the great talk. And the floor is now open for questions. Maybe I'll, since there are no other questions, maybe I'll ask a question. So it looks like the main idea behind both SCAFFOLD and Mime is the following, that if each client does multiple updates, there's a drift from the correct thing. So you have to fix that drift somehow. And in order to fix that drift, the clients are not able to do it locally because you need global information, and you need to modify the client updates to incorporate some global information. So in SCAFFOLD, you're basically compensating with the right thing, the CI minus C. And in Mime, you're doing it more indirectly by having this server momentum being applied at the client side. So is that a reasonable summary?
I think that's like a fantastic summary of. I should have probably said the same thing myself, but you're absolutely right. Yeah.
Thanks.
Yeah.
I have a question.
Yeah.
So how does this both SCAFFOLD and Mime perform as compared to centralized learning? Do you have any experiments or analysis?
So it's actually very difficult to beat centralized learning. So by centralized learning, I assume you mean you gather all the data on the server and just run a standard optimization method. And it's almost impossible to beat get accuracy as good as centralized learning. So so this is kind of a fact of life that we have to live with in federated optimization. However, we do observe that applying these kind of mitigation techniques, either the control-variates or momentum, enables us to get fairly close to central. There is still a little bit of headroom, at least in some basic some standard data sets that we have applied it to. But it gets close, but it's basically impossible to beat centralized training.
I see. Okay, thank you.
I had another question. So for your first algorithm, you're simply averaging all the gradients you have achieved throughout the algorithm from beginning to the end, right? So why putting more weights on the recent gradients rather than the earlier gradients?
Sorry, let me understand. So let me clarify one thing. So in a SCAFFOLD algorithm, we only average, in order to compute the control-variates, you only average the k local updates that you made in the previous iteration. So you don't actually compute it from beginning to the end, as you mentioned. So it's only in the previous iteration. You could certainly imagine, doing some kind of exponential moving average and averaging over the past few iterations as well.
Yeah, that's
but that's not what we do here. We just simply take from the previous iteration.
Yeah, that's what I'm saying. Would like help if you also add some information?
I see. Potentially, yeah. I mean, we did not experiment with that. It's possible that it might help. Analysis will be considerably harder, so we didn't consider this. So it's certainly possible. I mean, I see the intuition. It's similar to how momentum helps in optimization. So it's possible that this idea also helps, but we haven't actually worked on this idea yet. That's a good suggestion. Yeah.
Okay, if there are no further questions, let's thank Satyan again.
Okay, thank you.
And hopefully I'll see you all next week in the next AI4OPT seminar.